All right, we are into lesson 6, areas under curves. So let's start with a definition. The area under the curve of y is equal to f of x from a to b is defined as the region bounded by the curve y is equal to f of x, the x-axis, and the lines x equals a and x equals b. So you can see that as shown below. So here's a, here's b, here's x equals a, here's x equals b, those two vertical lines. Here's y is equal to f of x. Here's the x-axis. The area is everything between those three. Now, just to be clear, area under curve is a little bit of a misnomer. It doesn't necessarily have to be below the curve in the sense that you're thinking. It just has to be between the curve and the x-axis. So we can have curves where the area is something like that. As long as it's between the curve and the x-axis, that is what we consider the area under a curve. That will be important later. All right, let's take an example of this. So example 1, shade the area under the curve f of x is equal to 2x plus 1 from 1 to 3. Oh, that's an easy curve. That's just a straight line. Okay, so 2x plus 1, well, 2x plus 1 has a y-intercept of 1, and it has a slope of 2. So I'm just going to quickly plot some points to make this line easy to draw. And boop, 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 boop. Going the other way. All right, so there's our line. And we want to sketch the area under the curve from 1 to 3. Okay, so I'm going to make some markers here. Here's 1. Just going to make this line a little bit thicker. Here's the line x equals 1. And here's the line x equals 3. So what we're trying to find is the area between those and, of course, the x-axis. So we're looking for this area right here. Now, how would I figure out what this area is? Well, first, we are going to use geometric shapes. So I could use the area formula for a trapezoid here if I wanted to, but I don't want to because I'm lazy. So instead, I'm just going to break this shape up into a rectangle and a triangle because those are easy. So the area of this shape is area of the rectangle plus area of the triangle. So area is going to be, well, area of the rectangle. If we look at this rectangle, it's 2 by 3. So it's going to be 2 times 3, length times width, plus area of the triangle. That's going to be 1/2 times the base, which is 2, times its height, which is 4. That's just area of a triangle. Hopefully you know that formula at this point. And 2 times 3 is 6, and 1/2 2 times 4 is 4. So the total area is 10 square units. All right, so that was using geometric shapes. Now C, let's take the integral of this, the fundamental theorem of calculus. This is going to tie us back to when we learned that. So normally I would actually have taught you this first, but because things are weird and our time was limited, I had to rearrange things. But part of the fundamental theorem of calculus links the integral, the definite integral, with the area under the curve. So what I'm doing is if I want to know the area under the curve for 2x plus 1, between 1 and 3, I take the integral from 1 to 3 of 2x plus 1. So what this does is I take that integral and I get that this is 2x squared over 2 plus x from 1 to 3. Luckily, those 2's cancel out quite nicely. And we do that from 3 and 1, so this is going to be 3 squared plus 3 minus 1 squared plus 1, which is 12 minus 2, or, hey, guess what? 10 units squared. Exactly the same. So what you can see is that if we take the definite integral between those two x values, that will give us the area under the curve between those two x values. Nice and simple. So now we're just going to have to worry about taking the integral. So let's do an example. Well, first, I guess, just to be clear, if a of x represents the area under the curve y is equal to f of x from a to x, then a prime of x is equal to f of x. So it's just saying that, hey, we can go backwards. If we get the area and we take the derivative, it should give us our function. And therefore, a of x is the antiderivative of f of x. If f is a positive function on the interval a to b, then the area under the curve, y is equal to f of x, from a to b is a is equal to the integral from a to b of f of x dx, which is equal to f of b, big F of b, minus big F of a. In other words, the antiderivative at b minus the antiderivative at a, where f is any antiderivative of f. This is, again, just what we just did. Nothing fancy. It seems more complex when you put it all in that terms, but it's the same thing we just did in the previous example. So let's look at example 2. So what I'm going to do is I'm always going to start by just kind of drawing this. So to determine the area under the curve for y is equal to x squared plus 3. So here's my grid, and x squared plus 3, well, it has a y-intercept of 3, and it's x squared. It's symmetrical across it's a quadratic that is symmetrical over the x-axis, y-axis, not x-axis, y-axis. So the curve should look something like this, and I am interested in it from here to here, from 2 to 5. So I'm interested in this area right here. Okay, so the area then is equal to the integral from 2 to 5 of x squared plus 3 dx. This is equal to, well, that integral is going to be x cubed over 3 plus 3x from 2 to 5. That's a terrible 3. Let's fix that 3. Which is going to be, well, I do my substitutions. This is going to be 5 cubed over 3 plus 3 times 5 minus 2 cubed over 3 plus 3 times 2. Now it's just basic math, just basic computation at this point. So that comes out to 125 over 3 plus 15 minus 8 over 3 minus 6, which is equal to 117 over 3 plus 9, which, if I get my common denominator, you should be able to reduce this all the way down to 144 over 3 units squared. It's area, so I should include that unit squared. There we go. Not so bad, right? Okay, let's try a trig version. So, if I'm looking at this guy right here, we've got 1 up here, and we've got 0 over here, and we got pi over here. It's sine, so it's going to look something like this. And I'm looking from pi over 6 to pi over 2. So the area I'm looking for is right in here. So what we get is area is equal to the integral from pi over 6 to pi over 2 of sine x dx. Well, this is a nice easy integral. This one's not so bad. The integral of sine x, the antiderivative of that, is negative cosine of x. And we're taking that from pi over 6 to pi over 2. So this is going to be negative cos of pi over 2 minus negative cos of pi over 6. That looks terrible. Fix that. There we go. And cos of pi over 2 is just 0. Negative 0 is just 0, so we don't have to worry about that. And this is minus, well, cos of pi over 6 is root 3 over 2, so this is negative root 3 over 2. Careful with negatives. Negative negative is positive, so we get root 3 over 2 units squared. Done like dinner. Dinner. Don't ask. All right, so that's another example there. Let's give you a try. So give this one a try on your own, and then check back and see if you got it right. So determine the area under y is equal to 1 over 2x plus 1 from 0 to 1. Okay, so the area we know is the integral from 0 to 1 of 1 over 2x plus 1 dx. All right, so we take our integral, and remember when we're given 1 over something like this, we can use our substitution method here. Let u equal 2x plus 1. Du dx is then equal to just 2. So dx is equal to, I can't write today, I'm struggling, is equal to du over 2. So what we get for this one, so if we just start taking the antiderivative, let's just get our f of x. So let's say f is the integral of 1 over u du. Over 2. Sorry. Again, brain is mildly malfunctioning right now. So when I take that, what I'm going to get is that this is equal to 1/2 1 over u. Oopsie. The antiderivative of 1 over u is the natural log of u. So what we get, if we actually take our area then, is going to be equal to 1/2 natural log of 2x plus 1 from 0 to 1. There we go. A lot of you probably could have seen this one in your head without using the substitution method, but I wanted to practice using the substitution method, so I did. You can't stop me. I'm in charge. They gave me this job, not you. Wahaha. I'm honestly just stalling while I rewrite this over here to give myself more space. I have no regrets. Alright, let's continue from here, shall we? So now that we've got our area there from 0 to 1, we can then say that area is equal to 1/2 natural log of 2 times 1 plus 1 minus 1/2 natural log of 2 times 0 plus 1. Okay, this gives me that we have ourselves 1/2. I'm just going to factor that 1/2 out of both of those terms, and then use this as natural log of 3 minus natural log of 1. So I just factored out the 1/2. And then I'm just going to use my quotient rule for logarithms to rewrite this as 1/2 natural log of 3 over 1, which is just log 3. So a is equal to 1/2 natural log of 3 units squared. Or, if you prefer, and I do, or you could rewrite this as area is equal to, we can raise this to the power of 1/2. So we could rewrite this as natural log of 3 to the power of 1/2, which means a is going to be equal to the natural log of square root 3 units squared. That is also a perfectly good answer. I personally like that one better, but they're both fine. Either one's good. There we go. Okay, question. What happens if the function goes below the x-axis? So as I said before, under the curve is a bit of a misnomer. It's really just saying, hey, what's the area bounded by the curve and the x-axis and the x limits, right? The domain. So if I want to say, hey, what happens if the function goes below the x-axis? Well, we're going to take the absolute value of the integral over the interval part that is negative, because we're not worried about that being negative. It's just part of the total area. The area should just be positive. So we'll just take the absolute value of that part of the integral, which means we're going to have to do this thing in parts. So that actually comes from one of our integral properties from when we first learned about the definite integral, or about the indefinite integral even, where if we find the integral over two different parts of the domain and we add them together, that will give us the total integral over that domain. So first thing we're going to need to do is I'm just going to draw this. So I want to know where my x-intercepts are. That's going to be important. So to get my x-intercepts, I have that y is equal to 3x minus x squared, which I can rewrite as negative x times x minus 3, which means my x-intercepts are 0, 0, that's 10, not 0, and 3, 0. Okay, I don't know why I started writing at this weird angle, but I did, and I don't take it back. So when I'm drawing this, wow, that was terrible. This video is going a bit off the rails, isn't it? All right, so to draw this, I have an intercept here, and I have an intercept here, and I know that this is a quadratic, so I know that it's going to be, that was my cat going insane. So I know it's going to look something like this, because it's a quadratic with a negative x squared term, so it's going to be opening downward. And so what I'm looking for is the area between 0 and 5. Well, here's the thing. My 0 is here, but I cross the x-axis at 3. So 5 is over here. So what I have here is I actually have a couple of different pieces. The area I'm looking for is all of this, but also all of this. So I'm going to actually have to break this down into two parts. Okay, so I'm going to actually be looking at two areas. I'm going to call this A1, and I'm going to call this A2. All right, I'm going to just solve for them separately. So A1 is the integral from 0 to 3 of 3x, there we go, minus x squared dx. So this is equal to 3x squared over 2 minus 1/3 x cubed from 0 to 3, which is equal to 3/2 3 squared minus 1/3 3 cubed minus 3/2 0 squared minus 1/3 0 cubed. That one's going to be easy. All right, so solve that out. This is 27 over 2 minus 27 over 3 minus 0. So what we get is we just get this as a fraction over 6. Again, I'll let you guys take care of that, but that's 27 over 6, or 9/2 units squared. All right, so that's our A1. Now we're going to need to do our A2. A2 is going to be the integral from 3 to 5. So A1 was only up to 3, A2 is up to 5, from 3 to 5. So the integral from 3 to 5 of 3x minus x squared dx, well, most of the work we've kind of already done, so that's nice. So it's going to be our 3/2 x squared minus our 1/3 x cubed from 3 to 5. So it's going to be exactly the same as the previous integral, just different substitution. 5 squared minus 1/3 5 cubed minus 3/2 3 squared minus 1/3 3 cubed. 72, oh, that's not 72, it's 75. 5 squared is 25 times 3 is 75 over 2 minus 125, that's 5 cubed over 3 minus 27 over 2 minus 27 over 3. All right. Just some simplifications now. This is 225 minus 250 over 6 minus 3 times 20. I'll just take care of this one pretty quickly. 3 times 27 minus 2 times 27 all over 6. I'm going to be all sneaksy-like. If I have 3 27s and I subtract 2 of them, I'm not actually going to multiply 3 times 27. I'm not going to bother. Why would I do that? This is going to be negative 25 over 6 minus 3 27s minus 2 27s is a single 27. Easiest way to do that problem. You don't always have to expand. Sometimes you can just be clever and find shortcuts. I love shortcuts. That's what math is all about. So negative 52 over 6, which you can reduce to negative 26 over 3, right? And remember though, oops, I shouldn't have A2 is going to be the absolute value of all that. So it's the absolute value of all of these things. In fact, I don't really like the way that looks, so what I'm going to do is I'm just going to erase this and just take that integral and then say A2 is the absolute value of negative 26 over 3. That's an easier way of writing it, which is, of course, positive 26 over 3 units squared. So, yes, it gives you a negative value because it's below the x-axis, but we don't care about that. We're just interested in the area, which should always be positive. Areas aren't negative. All right, so our total area comes to A is equal to A1 plus A2, which is 9/2 plus 26 over 3, which is 27 plus 52 all over 6, or a final answer of 79 over 6 square units. Boom. And that's it. That is how you take the areas under curves using integrals. All right, go to your homework. Bye.